Okay, there are more things other than just velocity, frequency, amplitude that we can describe about waves. So if we compare these two waves shown on the screen at the minute, you should see everything about them identical. Okay, they have the same amplitude here. They have the same wavelength here. But there's something else we can compare about these waves, and we can just pick a point on the wave. So if we pick the wave at 3 centimeters along, okay, in our distance here, so this would be 3, you can see that this wave has a crest. And if we go here, this wave has a crest. And what we would say about these waves is they are doing the same thing at the same time, or another way of saying that would be they're doing the same thing at the same position. So if we have these two waves, they're identical in every way. So when this, at 3 centimeters, when this wave is up, so is the second wave, okay, when it's experiencing a crest. The other wave is experiencing a crest. Now, you have to remember this graph is just kind of a picture in time. So later on, this point in the wave, if this is a water wave, that part would dip down and then it would go back up again. But so would this one. So when this is a crest, this one here is a crest. When this is at the middle position, so would this one. When this is at a trough, or maximum downward displacement, so would the first one. Okay. Where that occurs, we say that there is a phase difference of 0 between these. Another way of saying that is they are in phase. Okay. Now, if we contrast that to the second set, okay, so if once again we go to the 3 centimeter point on both these waves, you should see now that it's not true. Everything else about these waves is identical, okay? Same wavelength, same amplitude. However, here and here, they're not doing the same things, okay? When this is having a positive displacement, the second wave is having a negative displacement. In fact, they're doing the opposite thing, okay? So in this case, we would say that they are out of phase or are in anti-phase in this very precise case, okay? Um, Now we can describe how much in phase or how much out of phase two waves are, or 2 points in the same wave are. We can do this mathematically. Okay, so if we look at this as our example, and we say, okay, to find out how offset they are, essentially, what we do is we find identical points on the two waves. Okay, so if I find that crest on the first wave, here's that crest on the second wave, okay? And if we kind of look at how much out of phase they are, well, it's from there to there, which is from what, 3 to 5. So that would be, you can see this is in centimeters. So I would say they are out of phase by 2 centimeters. But in fact, that's not very helpful, okay? It doesn't tell us, as we're going to see in later units, how those two waves would interact. By saying it's 2 centimeters doesn't tell me that when this one has a crest, the second one has a trough. So the other piece of information I could include is, well, how much is a wavelength? And if we look here, the wavelength is 4 centimeters, okay? And what I can say is, okay, well, it's 2 centimeters out of phase, but a wavelength is 4 centimeters. So what fraction of a wave is it out of phase? And I would just go, well, that's 2 divided by 4, which is, they're basically half a wave out of phase. And that's a much better way of describing it, because that does tell us how they interact. That does tell us that, okay, if it's a half wave out of step, when one has a crest, the other will have a trough. Now, the other thing we can do with that is we can represent that as an angle. Okay, this isn't going to make much sense, and the reason it doesn't make much sense is actually we don't use the proper equation to describe waves, and when we do, we use sine and cosine functions to represent waves. And if you imagine an entire sine or cosine wave, we get a full wave over 360 degrees. Okay, so if this is sine of x and x goes from 0 to 360 degrees, you would get a full wave in that space of time. So what we can do with this half a wave is we can say the phase difference is half a wave. However, I can say that a full wave is 360 degrees, therefore a half of 360 degrees is 180 degrees. So I can say, rather than saying it's half a wave out of phase, I can say it's 180 degrees out of phase. To complicate things even more, there is another unit for measuring angles that you may have come across. You definitely come across it at A level. I'm not sure if you come across it at further maths in GCSE, called radians. Okay, and it's just another unit that has its uses. But basically 360 degrees equals 2 pi radians. Okay, it's just another unit in the same way we can make conversions from like feet and inches into centimeters and meters. We can do the same thing with degrees and radians. In fact, to be honest, in physics and maths, this one's the more used term. So therefore, if I'm measuring it in degrees, I multiply the fraction of a wave that it's out by a full wave in degrees, and it gives me 180. To do the same thing in radians, I would just multiply a half by a full wave. 360 degrees in radians is 2 pi, which would tell me it's pi radians out of phase. This, and this are all the same thing. Okay? It might just ask you what's the phase difference. Pick what you like. It might ask you what's the phase difference, and there might be a blank, and it might say degrees, or it could say radians. Okay, and you'll have to give it whatever they want. Now, in this instance, we have compared these two waves. Okay. However, you could be just asked to compare 2 points in the same wave. So, for instance, if I compared this point and this point, well, they're doing the same thing at the same time. They are in phase. Let's do between this point and this point. If I do that, if I just forget about the bottom wave, and we're just comparing 2 points in the same wave and seeing how out of phase they are, we do the same thing. So I would say a full wavelength of this wave is still 4 centimeters. The difference between our first point and our second point there is just 1 centimeter, which means that they are, just go up here, a quarter of a wave out of phase. Okay, but I can represent that as an angle in degrees. So a full wave is 360, therefore a quarter of a wave will be 90 degrees. Or likewise, I can represent it in radians, where instead of using the 360, we use 2 pi, and that would give me that it's pi over 2 radians out of phase. Okay. These are the steps here that we go through to do this. For some reason, pupils find this difficult, and I don't know if it's just one of the first things we do, and our brains aren't quite working after the summer yet. This is, to me, is not difficult. It's quite simple. Whenever I mark papers, lots and lots of people get this wrong, and it's worth a fair few marks as well most of the time. So, do make sure you practice this, and that you can do it in either degrees or radians as well, because you don't know what they're going to ask. So for the first one, we would say they are in phase. Another way of saying that would be they are 0 degrees out of phase. For these two waves, we would say they're 180 or pi radians out of phase, which means they're in anti-phase. When one's up, the other one's down, essentially. So we have our steps here. Use these to try and answer this question and this question, and then I'll post the solutions below.